All right, so today we're going to finish up really briefly here with recursion by looking at how to do memoization, or a little bit better way of doing memoization in Java, because you have this rich data structure called a map. And but I also wanted to take it as an opportunity to show you the use of big integer, which is a multi-precision integer version in Java that allows you to express numbers that are arbitrarily large. So if you only have 32 bits, right, and you try to have a value that's greater than that, you're going to overflow. And what happens with big integer is if you end up overflowing, it'll just allocate more memory for more bits, right? So again, if you have any questions, you're going to go ahead and post the YouTube live stream here, though. So what we're going to do is we're going to compute the Fibonacci sequence here. So public static, but instead of returning an int, instead of returning a long, both of which Java supports, we're going to return this built-in type. It's not built-in, but it's in the standard libraries, big integer, right? Fibonacci, and of course we're going to want to do memoization right off the bat, because if we have very arbitrarily large numbers, then of course it's going to take centuries or thousands of years to compute these things. We will take an integer n here, but also we'll take a map. And the interpretation here is that this will be an input to the Fibonacci sequence. So an integer, right, f of n, is going to map to a big integer, right, the value of the Fibonacci sequence. And so this is my cache, okay? And let's go ahead and import this. Oops, come on. Oh, okay. It's not going to let me do that until I actually return null. And then it'll let me import it. There we go. All right, java.math is where it where it lives. Right, there's a big integer. There's also a big decimal, which is an arbitrary precision floating point number. But since the Fibonacci sequence is an integer, we'll go ahead and go with big integer here. All right, so the first thing we do is we check that map. If the cache.get n, right, is not equal to null, what that means is that the value for Fibonacci of n has already been computed and has already been put into the cache. So we're just going to go ahead and return it. Return cache.get n. Okay? And otherwise, we'll pay for the recursion, right? So the Fibonacci sequence is going to be Fibonacci of n minus 1 plus Fibonacci of n minus 2. So let's go ahead and do that. Big integer a is equal to a call to Fibonacci on n minus 1, passing in the cache unchanged, right? And then we're going to get the other one. Fibonacci of b is going to be n minus 2, the same cache. Now my result here, big integer result, is equal to a plus b. That only works for built-in types, right? Integers, doubles, floats, etc., longs, right? That built-in operator, the addition operator there, it will only work for those built-in types. So if you've got this big integer, what you have to do is you have to invoke a method. A.add, another big integer, b. Right? Okay? That returns a new big integer, which I store into result here. Okay? We want to make sure that it's in the cache, so cache.put n maps to result. And then we can finally return the result. There we go. All right. That's it. That's as simple as that. Now let's go ahead and test it. All right, so big integer result is equal to Fibonacci dot Fibonacci of n, and then we need a cache here. So now we actually have to build the map, right? We have to build our table of values and take care of our base cases. So my map here will map integers to big integers, and I'll call it cache because that's what it is. It's a new hash map, and I need to make sure that I'm taking care of those base cases where Fibonacci of 1 is 1 and Fibonacci of 2 is 2. Is that how we did it last time? I don't remember. We may be off by 1 or something, but cache.put, I will go ahead and map 1 to 1 and cache.put map 2 to 1. Now that's not going to, oops, I misspelled it, but that's still not going to work for other reasons, right? So let's go ahead and look and see what the error message here is. So putting an integer mapping to a big integer doesn't work when they're both integers, right? This thing right here is an integer, right? It's not a big integer. So what do I do? Well, fortunately, 1 is a very special number that's used all over the place. So big integer dot 1 is well represented here with a built-in variable. 0 is also, and I think 2 is in there as well, because those are the two common things that you do. You always add 1 or subtract 1 or add 0 or compare it to 0, etc. Right? So let's go ahead and see if this works by printing it out. System.out.println of Fibonacci of concatenate n, concatenate that equals, and then concatenate the result. Automatically it will be dumped to a string representation base 10. So I forget what the 10th Fibonacci number is. It's like 55 or 89, whichever one it is. Hey, there we go, 55. So let's come over to Wolfram Alpha and look at something very, very large, like say Fibonacci of 100. This is even larger than we would have been able to do with a long in C, right? And it starts with a 354, ends with a 075. So keep that in your mind there. Otherwise, we can go back to it. 354, 075, it looks like to me. And instantaneous. Now you kind of know how Wolfram Alpha is doing this. Let's go ahead and get crazy. 10,000. Right? So many, many, many digits. Just pay attention to the first 3 and the last 3, right? Or at least the first 3. 3364, or first 4, I guess. So 10,000. I'm crossing my fingers here. Why? It's probably not going to work. And it didn't. Why? There's a huge stack trace here. And what was the problem? Stack overflow. Right? I was still doing recursion here. Right? I was cutting out the redundant recursions, but I was still doing recursion. I was still doing 10,000 function calls. Right? That's way too much for the Java stack, apparently. Right? So yeah, 10,000. That's quite small, but it looks like maybe the stack frames are much larger in Java, so we're not even able to do 10,000 here. So what's the final? What's the actual solution to go about doing something like this? Iteration, exactly. Right. You don't abuse the call stack and let it overflow like this. Okay. All right. Questions on that? Yeah, go ahead.
Is there any time that you would say that memoization is better than iteration?
Maybe when it's so complicated that you, not really, because the next step is dynamic programming, where you realize, wait a second, if I'm keeping track of this table anyway, why the hell am I doing anything recursively? It's just a table. I just need to fill out that table. I just need to figure out in what order do I fill out that table, right? And at that point, you eliminate the recursion. That's called dynamic programming. That's it, right? So, but more generally, is there any time when recursion is better than the alternative? You can say that a lot of things get simpler when you use recursion, especially if you have, like, say, hierarchical data, like a data tree, like a document, right? Or like a web page, HTML document, where you've got this root, and then each node in your tree has children, and you want to do the same operation over and over and over for all of them. Even that goes out the window once you see a stack-based recursion on it. You put stuff, you got this stack, you put stuff in, you take stuff out, and it's done, right? So I've never seen ever one where I would argue, oh yeah, that is way better recursively than this over here, right? I don't know, maybe post-order traversal because there's a little bit more information to keep track of, but not really. 10,000, can't even do that. 1,000, can't do that. I wonder what our limit is. 750? Nope. Geez, come on, 500? We were able to do 100. Oh, I'm not saving. Duh. Yeah, okay, there we go. We were able to do 1,000. 4346. I'm sure it's right. 4346, right? And instantaneous. And we were able to get by with recursion there. Right? Okay. Any questions on that? Otherwise, you got to see some cool stuff, right? You've seen maps before, but now you see their real power. You don't have to worry about indices or anything like that. You can just go ahead and map whatever you want to whatever you want. You've also seen, let's see, what else? Oh, big integer, right? So if you ever do need arbitrarily large numbers that are hundreds or thousands of digits long, big integer is your solution. Now, it comes at a cost. All that stuff is being done in memory instead of hardware. An integer plus an integer, that's done in hardware super, super fast. This is not done in hardware. It's done piecemeal in hardware, in software, and that's way more expensive. That's going to be way more time consuming. All right. So we will get started on the last module for this course. We will be focusing on this for at least 2 weeks, maybe all the way to the end, I don't know. But it's searching and sorting, and so it's going to be our first formal introduction to actual algorithms. And these two operations, searching and sorting, are fundamental to all data processing. Just as, you know, plus, minus, multiplication, those are fundamental to math because they're arithmetic operations. When you're processing data, the two most basic things that you can do is search for something, and then you have a collection and you put it in order, right? You sort it. Right? And those are the two fundamental operations that we're going to focus on going forward. They form the basis or a pre-processing step for pretty much most algorithms, because a lot of algorithms will say, we'll assume that these things are in order, and then we'll go from the least to the greatest because it gives us this property that we're looking for or something, right? And it provides an opportunity to look at a large variety of different types of algorithms and algorithmic approaches. Decrease and conquer, divide and conquer, brute force, et cetera, et cetera, et cetera. Right? What I want to do is I want to start out with a very, very simple exercise. Right? I want to find a needle in a haystack. So if this doesn't load up really quick, we can do it in Java instead. You've done this now a couple of times, right? You've searched an array of stuff. You've searched a string for a particular character, right? So when I say searching for stuff, what do I mean? Right? So preliminaries. Right? What does searching mean? Right? What are you searching? What are you searching for? Right? And, you know, what are you searching, and what are the elements you are searching? There is a difference there, right? So what are you searching? I'm searching an array, or I'm searching in a list, right? An array, a list, right? You could also search a set, right? We've looked at those before in Java. You could be searching a map, right? Et cetera, et cetera. What are the elements that you're searching for? Well, we've kept it simple up till now. Are you searching for an integer, right? Double, right? Are you searching for a character, right? Are those the elements that you're searching for? And how are you, let me rephrase this. What are you searching for? How are you searching for it? Right? For example, you can find a particular element, say X. Just give it a label, right? That's not the only way that you can search, right? You've searched before for, say, the maximum element, right? Find the maximum or minimum element. Find what's another extremal element? Not just the max and min, but what's right in between? The average would be like adding them all up and then divided by n, but what's right in the middle? If they were all sorted, right? What's right in the middle? The median, right? Find all instances of a particular element, right? And then we can throw another wrench into the whole thing, and suppose that we're not just searching for primitive types, integers, doubles, characters. What if we're searching for airports? Right? What if we're searching for teams, right? Well, then how are you searching for them, right? Are you searching by NUID? Are you searching by name? Right? Are you searching by GPA, right? If they were a student, right? For your airports, how could you search for something? You'll be doing it after the break. By latitude and longitude, find the northernmost, find the easternmost, right? Latitude and longitude for distance. What's the closest airport to this particular location, right? That would be Lincoln Airport, probably. Lincoln Municipal, is it called? Okay, whatever it is, right? So what are you searching for? How are you searching it? Let's go ahead and keep this simple. And I'm going to get rid of all, that's not ours, so I won't get rid of all of it. There we go. All right. Let's keep it simple and start out with the most basic, right? Suppose that we have an integer array. And I'm going to put stuff into it. 4, 9, 3, 8, 6, 2, 1, 1, 2, 3, 4, 5, 6, 7, 8. There we go. There we go. And there are 8 things in there, unless my eyes deceive me. Okay. What's another thing that you could do? You could search for all instances of, say, 9 in this case, right? You could search for the first instance. You could search for the last instance. Right? We need something to go on here to get started. So help me out. To do search for a key, right? A particular key. Let's say, I don't know, int key is equal to 1. So we call this we call it a key because it unlocks a door. You're finding an element that matches that key. Okay. You are searching through a haystack, right, the array, for a particular needle. In this case, 1. Right? So how would you go about doing this? First of all, should we be doing it right here? Well, let's write a function to do it. Right? Search for. I'll go ahead and call it search for now. And what are we going to take? We're going to take an integer array, const int star array, and the key element that we're needing to search for, but also the size of the array, right? Int key. Right? So let's document what we're doing here. This method, or this function, searches the given array of integers of size n for the given key. Right? If we're successful in finding that element that matches that key, what should we return? I found it. Eureka. I didn't find it. We're searching for 42. Unsuccessful search. What's one option? A Boolean, right? In C, we'll just use an integer, right? So it could returns true, false, if it found it, right? You've done that before, right? You already did that one. It was called contains. Contains, right? You did that on hack 7, I believe. Right? Does it contain that particular element? Does it contain that particular element within these two index bounds, right? Okay, you could do that. What's another option? What would give me even more information? Right? If I look at this one, if I said, yes, 1 is in that array, does that help you find out where it is? Nope. So what can we return instead in that case? To give you more information. Not only is it in the array, but it's at this location that you can find it. No? Index of, right? Get the index of, right? So it returns the unindex at which key is stored. Right? What's another option? It's over there. What am I doing? I am pointing, right? So it could return a pointer to the memory location at which key is stored. Right? Which one do we want to do? pointer? Okay. Let's go ahead and do that. Int star, index of. Now help me out. So this is the one that we're doing right here. What should I do? For int I equals 0, I is less than n, an idiomatic for loop, right? I plus plus. Just start at the beginning and start asking questions. Is that it? Nope. Is that it? Nope. Is that it? Nope. Nope, nope, nope. Yes, done. So if array sub I is equal to the key element that you're searching for, you found your needle in the haystack. Stop and return something. If we get through the entire array and never find what we're looking for, 42, right, we get to the end. What should I return as an indicator that it does not exist? Return null. Why? Because it expects a pointer. And the only pointer that has any meaning other than the meaning of something went wrong or it doesn't exist or nothing is null. Right? What should I return here? I? Actually, if I went with the first version here, I would end up returning true or 1. If I went with the second version here, what would I return? I, the first index at which I found it. But we decided to go ahead and go with this version right here. Return a pointer to the memory location at which it's stored. How do I get the memory location of this guy right here? Is it that? Well, no, that just gives you back your key, right? Where's 1? Here you go. Here's 1 again, right? So an unhelpful, store clerk or something. Right? All right. So how do I get the memory address of a regular old variable? Ampersand. Right? There we go. So now let's use it down here. Right? Int ptr is equal to index of, pass in the array, pass in the size, and pass in the key that you're looking for. Right? And printf, or if ptr is not equal to null, that means it was a successful search. Printf, found element %d at memory location %p and the line. We're searching for the key and we were given that pointer. Okay. And then we can add more information to confirm, right? Which holds value %d, and then dereference that pointer variable, which is safe because we checked for null here. Else, if it's null, then printf not able to find key %d and the line key. Right. Good. That's a good first version here. GCC demo. Oops. Yeah. Don't worry about that. All right. Found element 1 at memory location blah, which holds value 1. Let's test it for an unsuccessful search here. 42. We should expect that it does not find 42, and so we would have not able to find key 42. What about 9? There are multiple variables of 9, multiple values of 9 in this array, right? So which one does it end up returning? Unable to tell here, right? But knowing how the algorithm works here, which one of these 9s is it pointing to? The first one or the last one? Well, since it starts at 0, it returns the first one right here. Okay? Awesome. You know what? Now I want to do the same thing, but for fractional values. 0.4, 0.8, 0.3, 0.2, 0.0, 0.4, 0.3. Right? Can I do it? Can I just go ahead and say brr, and I'm looking for 9.3 now? Change that to a double. That should be a double. Right? Is this going to compile? Probably will, actually. But is it going to get me what I want? Probably not. Why? These are doubles. What did I write this function for? Integers. Okay, well, code reuse. Copy, paste. Index of 4 doubles. Right. What changes would we need to make? This takes a double, this is now a double, and this is a double. Do I change anything else? Nope. Okay. Now I want to search strings or characters. Right? Now I want to search for students. Now I want to search for something else. What's going to change? Just the prototype. Right? I'll have an index of for integers, an index of for doubles, an index of for strings, an index of, and an index of, and an index on. Does that sound like a good, kind of design principle to just cut, paste, cut, paste, cut, paste, change one little tiny thing? Right? Nope. We're going to look at a much better solution later on. Okay? But before we do that, let's understand what we just did. Right? What we just did is an algorithm called linear search. Right? So the basic idea is that given a collection of elements, right, and a key element k, search through the collection and find an element that matches, and I'll put that in double quotes here, matches k. Because that goes back to all these preliminary questions that we had. Well, first of all, what's your collection? Is it an array? Is it a list? Is it a set? Is it a map? I don't know. What are your elements? Are they integers, doubles, airports, teams? Right? What does it mean that it matches that key value? That you're searching for a particular element, that you're searching for the minimum, the maximum, right? Are you, if it's students, is it by NUID? Is it by name, et cetera, et cetera? I want to keep this general. Because what I failed to do over here in C, of writing one version of this function to rule all, right? I'm going to succeed over here using what's called pseudocode, right? So we'll start with pseudocode, right? Fake code that is not tied to a particular language, right? It doesn't use language specific notation, right? It makes use of math notation because it's abstract. It's abstract and general, right? Good pseudocode can be translated into any particular programming language, right? In other words, it's going to be our Latin, where it's the base root of any programming language, right? Now, is it a programming language itself? No, there are no rules for it. They're just general guidelines. If there were rules for pseudocode, guess what you would have? A programming language, right? And we don't want that. We want to keep things general, right? So let's go ahead and I've got it over here. Hopefully it's still up. Come on. You know what? Let me bring this up so it's on the same level. So I'm not leaning over. There we go. All right. So I've got my tablet with me today. All right. Let's go ahead and write some pseudocode here. And this is why I'm switching over here to writing by hand, because I don't want to type this out. If I ended up typing this out, it'd probably look a lot like Python or something, right? And I want to get away from any particular programming language. So what I'm going to do to write good pseudocode is I'm going to identify the input and I'm going to identify the output. My input here is a collection of elements, A, and here I'll label them A1, A2, ... AN, and a key K. All right? Now what have I done here already? Have I specified that this is an array? Nope. List? Map? Nope. I've kept it generic. I've kept it general. What have I done here? I've given them an order implicitly, at least with respect to these subscripts here. But I've done it in a mathematical way. Do we start at 0? Like decent computer scientists? Nope. We start at 1 like mathematicians. But we also tell you how many elements are in that array, or in that collection, excuse me, immediately, right? By labeling it. Right? Okay. Our output is going to be, well, what do you want to do here? An element A in A such that A is equal to K. What does it mean that it's equal? Am I using equals equals? Nope. Am I using some, strcmp function to say that this thing is equal to this thing because they're the same string contents? Nope. Am I using dot equals? No. I'm keeping it generic. This can mean anything that you want when you ultimately translate it to whatever programming language you're implementing it in. Right? What if we don't have such an element? Phi if no such element. Meaning that I'm not going to output, I'm not going to return null. I'm not going to return, by the way, if we had chosen another way, right? If we had chosen this way, return an index at which the key was stored, what would we have returned if we didn't find the element that we're looking for? -1 would be reasonable, right? Because that's not a valid index anywhere. Right? So I'm not returning any of that stuff. I'm returning this mathematical symbol phi. Okay? All right. I am not bound by the traditional for loop. Instead, what I'm going to say is for each element A in A, right? And I will use it, too Python-y. Right? In Python, you define a block by colon, and then everything in there is your block. They don't have opening and closing curly brackets. I'm not going to have opening and closing curly brackets here. For each A in A, if A is equal to the key element K, then I will output A. A couple of things I did there. Right? Again, I avoided a traditional idiomatic for loop. I'm not using a while loop. Right? I'm not using any syntax that would be recognized in any language because I want to keep this general and generic. If A is equal to K, I kept a generic equals there. Right? And then instead of returning, because this is not a function that you put a prototype and a definition in, it's not a public static void function, right? It is an algorithm, right? This is pseudocode. So I'm going to say that it outputs A, because that's what an algorithm does. It outputs something. There's input and there's output. So if you find an element that matches, then you output this thing, okay? Otherwise, if you get through everything, you output phi. Another thing that I did there, what is this and what is this? That's how I'm defining code blocks. I stole that from LaTeX, and I really like it because, first of all, can you type that at all? No. But modern IDEs have also stolen it, because what can you do? You can collapse blocks of code like this in some IDEs. And how does it denote that code of block? If you look really, really hard, you see this vertical line with a little thing at the end to indicate that it only goes down to here, right? When you hover over it. See it? Can you see it on that big one? Okay, I don't know if it's too light or not. Right? But that's what I've done over here. Right? Now, when I write pseudocode, I usually write it in LaTeX, and the LaTeX package to do that actually has strict rules because otherwise it wouldn't be able to format it correctly. So it ends up being a programming language, and that you can program in LaTeX if you want to. Nobody in their right mind would want to do that, but you can do that. Right? This is good pseudocode. I'll label it. Good pseudocode. Now we understand what pseudocode means. Well, what's the root pseudo mean? Pseudoscience or pseudoephedrine or something, right? What does pseudo mean? What? Not real, fake, right? It's fake code. It's not real code. It's just generic. It's a generic expression of what an algorithm is, okay? Now what I want to do is I want to analyze this. So off to the side here, analysis. I'm going to come at this from a best case scenario, a worst case scenario, and maybe something in between. Right? So what we need to do is we need to capture the idea of what this algorithm is doing as far as work. Right? So what work is the algorithm doing? Right? If it helps, think more in terms of this over here. I've got an integer I that I initialize, so I've got an assignment operator here. I've got a check to see, should I keep going in this loop or not, right? I'm making a comparison there, right there. That's some work, right? By looking at those two values and saying, okay, well, this one is strictly less than that one, so keep going. Right? And by the way, at the end of the loop, I'm going to be adding 1 to this value over here, so I'm doing an addition. We generally don't look at those things, though. Those are necessary for the control structure of the algorithm. What actual work am I doing here? Is that thing equal to that thing, my key? Right? So, my work here is a comparison. And I'm going to label it. Which line is it on? 1, 2, 3, and 4. On line 2. Okay? Now let's analyze it with respect to the number of elements in that collection, right? The number of elements right here. So let's think about the best case scenario. Actually, let me rephrase the question first, right? How many comparisons are made by this algorithm, which we have yet to give a name to, by this algorithm, algo for short, in the best case? So in the best case, what would happen? Yeah.
N minus whatever 2 is.
So the best case would be doing the least amount of work. If our work is measured with respect to comparisons on line 2 here, how can we get away with the least number of comparisons? If it's the first thing we find, right? If it's the first thing we find, how many comparisons do we end up doing? 1, right? It's the first one, first place we look. That never happens though, right? You're searching for something, your car keys or something, and where is it? It's always in the last place that you look. Well, that's a tautology, right? Because you're not searching for it anymore after that. So even in the best case, it's in the last case, it's in the last place that you look, right? Let's go the other way. In the worst case, now how many comparisons do we make? Is that it? Nope. Is that it? Nope. Is that it? Nope. Is that it? All the way to the end. We didn't find what we were looking for. And we end up outputting, nope, didn't find it. How many comparisons did we end up having to make then? How many elements are in the collection? N. Right? So in the worst case, we make n comparisons. Okay. Now, is there a happy medium, right? Because you're not always going to get the best case, right? You can't be optimistic, but you can't be pessimistic either, right? Sometimes you'll find it in the middle. Sometimes you'll find it at the second place that you find it. Sometimes you'll find it in the second to last place in the array or in the collection, right? So what would we call that maybe? Expected or average? Average case? Now, for a full actual analysis of the average case, you would want to define a probability distribution on finding stuff, and then the number of comparisons based on that probability distribution. Then you would want to maximize that distribution, the number of comparisons with respect to that distribution, blah, 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 right? We're not going to go there because you end up at the same result if you just be naive about it. The average case, if you just take the best case and the worst case and you average them together, right? It'll be about that. Now, that 1/2, I don't want to pay attention to 1/2, right? Nobody makes 1/2 comparisons, right? Make a comparison or you don't. So I'm going to simplify this to 1/2 n. Okay. Let's focus on these two and graph them. Oops. Straighten up. There you go. So what I'm going to graph here is n. This is the size of the collection or the array. Right? And here, y is going to be the number of comparisons. So if I were to graph that worst case scenario, what would it look like? There we go. Yeah, wow, it even snapped a 45-degree angle there. Cool. Right? This would end up being n. Right? This is the worst case. What would the best case look like, by the way? Something like that. Always stays the same. We're not going to look at that, though. What does the average case look like if I treat it as 1/2 n? No? About like that. Right. That's n over 2. Right. Why is that? Well, the slope, right? The slope here is 1. The slope here is 1/2. Right? Who would have thought that graphs come in handy here, right? But tell me about those two functions. Are they really all that different? So now put on your calculus hats for a moment, since this is the honors section. Right? I'll assume that you've got some calculus. How can you quantify the growth rate of a function? How fast is this growing? How fast is this growing? Growth rate of, say, n. What's the tool that you use for a growth rate of a function? First derivative. First derivative of n is equal to 1. All I'm doing is using n instead of x, if you want to think of it as x. Okay? What's the growth rate of 1/2 n? 1/2. Now look at those two numbers. They're both constants. Right? In other words, it doesn't matter if you look at this from the best case scenario or the worst case scenario or the average case scenario. Right? These are both constants. The growth rate is constant. So the growth rate is constant. Now, tell me about those functions themselves. What kind of functions are those? It's not like this, like n squared. Right? That would be a quadratic function, right? What are these functions? They're linear. Linear. Both are. Okay? They have a constant growth rate, and they're both linear functions. For that reason, we now have a name for this algorithm right here. Right? This is linear search. Why is it called linear search? Because it makes a linear number of comparisons to search the array or to search the collection. In the best case, in the worst case, and in the average case, it doesn't matter, right? And therefore, I mean, look at the growth rate here. Suppose that I had, say, yeah, we're good, but we're gonna have to cut it short because I forgot to plug it in. Pretty good that it ran OBS for almost an hour here on one charge. Excellent, good job, Mac. Right. Anyway. Consider the following. So if I have an array, a very, very large array of millions, billions of elements, I'll just make that generic and say that it's n elements. And suppose that it takes time t to actually search through it, right? So this is the size, and this is time t. Now suppose that I double the size of the array, or double the size of the collection. I go from, say, 10 million elements to 20 million elements, okay? So now it's 2n. What would you expect the time to be now? How much time should it take now? Twice as big, 2t, right? What if I went from n to 10n? Right? In other words, I went from 1 million elements to 10 million elements. What would you expect the time to be now? 10n, or 10t, excuse me. Right? In other words, because it's linear, if you go up in input sizes, the cost in time is going to be greater. It's going to take longer time. But it's all going to be proportional to the size of the input that you give it, right? That if you increase it tenfold, it took 1 second before on 1 million elements. You can expect it to take about 10 seconds now on 10 million elements, right? That allows you to predict it out and to predict how much time it's going to take, right? The number of comparisons, which is equal to the time, right? Because each comparison takes, I don't know, 0.005 nanoseconds or something like that, right? And if you double it, right, if you go from, say, this to this, right, that means that it's going to double in size because it's a linear growth, right? Can we do better? Right? So for that, I will leave you with a classic Price is Right game, right? So the price, it's just a game show if you're not familiar with it. It's still on, right, during the day, but you have something that you have to guess the price of. And they tell you, well, it's between $0 and $100. Now, if you guess the price in the next 5 seconds, I'll let you guess as many times as you want, but if you guess the price in the next 5 seconds, well, you win the prize. So what's your strategy for guessing? Is it $1? Is it $2? Is it $3? Is it $4? Is it $5? Is that going to get me anywhere? Nope. I'm also going to tell you whether or not your guess is too low or too high. Now what do? Right in the middle, right? Is it $50? No, it's higher. Now what? Is it 75? Lower. 62, somewhere in there? Okay, higher. Between 62 and 57, 75, I don't know what that is. Anyway, I was thinking of 67, right? So what are you doing? You are honing in on it, right? By looking at the middle element. But what did you need? You needed a range from $1 up to $100. That way you could jump into the middle. Is that going to work with our array right here? Am I going to be able to jump in the middle and have any information on where that element 1 is? Nope, because it's not sorted. But if it were sorted, I could take a strategy that looked like that. Right? And that's what we'll look at on Friday. It's called binary search if you've seen it before. All right, see you on Friday.